You know that feeling when you search for a contact on your phone and it just appears? Or how a website seems to remember who you are, instantly? Well, that feels like magic, but it's not. It's one of the most useful tools in all of computer science, the hash table. Today, we're going to pull back the curtain on this invisible engine that makes our digital lives feel so incredibly fast. Let's get into it. So to really get why hashing is such a game changer, we first have to understand the problem it was designed to solve. And we're going to start with something I think we can all relate to: being stuck in a painfully slow checkout line at the grocery store.
Okay, so picture this. You're the cashier. A customer comes up and puts an apple on the counter. You have no idea what it costs, so you have to grab this huge, heavy price book. And if that book isn't sorted, you're stuck scanning it page by page by page trying to find the word apple. It's slow, it's boring, and you can just feel the line getting longer behind you.
Now, this is where things get wild. Let's say our book is sorted alphabetically. Now we can use a much smarter method called binary search. Basically, you open the book to the middle and immediately know which half your item is in. Look at the difference this makes. With a billion items, that simple line-by-line search would take about 30 years. Yeah, 30 times years. But a binary search? 3 seconds. That's a massive improvement. But we can do even better. We're not looking for fast. We're looking for instant.
So what's the dream solution here? What if we could just forget the book entirely? What if lookups could be completely, totally instant?
Let's just imagine you have a coworker named Maggie. And Maggie's amazing. She has every single price for every item in the store memorized. You just yell, "Hey Maggie, price on an apple," and she instantly shouts back the answer. No searching, no waiting, just the answer. That's the goal.
This chart just says it all. That huge bar on the left, that's our slow, painful, simple search. The next one is that much better binary search. But look at the bar for Maggie. It's practically a flat line. In computer science, we call this O of 1, or constant time. And what that means is, it doesn't matter if you have 10 items or a billion items. The lookup time is always the same. It's always instant.
Okay, so Maggie is fantastic, but she's not real. The real question is, how can we build our own Maggie? How can we use data structures to create this magical instant lookup system for ourselves?
And this is where hashing comes in. It's not magic. It's just a really, really clever system. And it's built on 2 key ingredients that work together perfectly. Let's break them down.
So ingredient number 1 is the star of the show, the hash function. Think of it like a special code machine. You put a word in, like apple, and it spits out a number. And here's the golden rule. It has to be consistent. Every single time you put in apple, it has to spit out the exact same number. Let's say for apple, it always gives you the number 3.
Our second ingredient is just a simple array, which is really just a bunch of numbered boxes or slots. So here's how they play together. We take an item, say milk. We feed it to our hash function. The function gives us back a number, in this case, 0. So we take the price of milk and we store it in our array in box number 0. We do the same for apple, and our function tells us that 1 goes in box number 3. It's that simple.
And that is the secret sauce. When you need to find the price of milk again, you don't search the array at all. You just run milk back through the hash function, it says 0, and you go directly to that spot. It's not a search, it's a direct address lookup. We've built our digital Maggie.
Now, this all sounds a little too perfect, doesn't it? Well, there's always a catch. In the real world, there's one major complication we have to deal with. What happens when our hash function gives us the same number for 2 different items?
This is what we call a collision. So imagine our hash function takes apple and says go to box number 1. Great, but then we give it avocado and it also tells us to go to box number 1. Both items now want to be stored in the exact same spot.
And that's a huge problem. I mean, if we just store the avocado's price in slot 1, we've just completely erased the price for the apple. Our whole system is broken. So, what do we do?
Well, the solution is actually pretty elegant. Instead of storing just one price in that box, we start a little list there. So when apple hashes to index 1, we put its price in the list. Then, when avocado also hashes to index 1, we just add it to that same tiny list. Now when we look for a price, we go to slot 1 and do a quick search of that little list. As long as our hash function is pretty good and doesn't cause too many collisions, these lists stay super short and our lookups stay incredibly fast.
Okay, so we've built our digital Maggie. We got the theory, but where do you actually see this in action? The short answer is absolutely everywhere. Let's look at just a few examples that you probably use every day.
Your phone's contact list, that's a classic hash table. A person's name is the key, you feed that name into a hash function, and it points directly to the value, which is their phone number and all their other info. That's why you can have thousands of contacts and still find someone instantly. No scrolling, no waiting.
Hash tables are also basically the foundation of how the internet works. When you type in a website name, your computer has to translate that name into a numerical IP address. That whole process uses hash tables to map the name you can read to the address the computer can use. It's like a giant super-fast phone book for the entire web.
Another really powerful use is preventing duplicates. Think about a system for tracking votes. When someone comes to vote, you add their name to a hash table. If someone with that same name tries to vote again, you can check the hash table instantly. The lookup is so fast, you know immediately if they voted before. Way faster than scanning a giant list.
And finally, caching. Big websites like Facebook or YouTube use hash tables all the time to store data that's requested often. So instead of having the server build your feed from scratch every single time you load the page, it can store a ready-made copy in a hash table. When you request that page, the server just grabs the cached version, which is crazy fast and saves a ton of work. It's why modern websites feel so snappy.
So, to wrap it all up, just look at this table. This is what makes hash tables so special. On average, they give you the best of both worlds. The instant search time of an array combined with the fast insertion and deletion of a linked list. It's just a remarkable combination of speed and flexibility.
And this quote really just nails it. It's not some niche academic tool. It's a fundamental building block of modern software. If you understand hash tables, you understand a core piece of what makes all technology feel fast and efficient.
So, from finding a contact to loading a web page, hash tables are the unsung heroes working behind the scenes. They're the magi we wished for, just built from logic and code. They take a slow, frustrating search and somehow make it feel like actual magic. And it really makes you wonder, what other invisible magic is powering the technology we use every single day?